And Min-Sung is going to close us out. I apologize for everyone for eating into the break a bit, but hopefully you can be patient. We'll start again at 11:20. Fred will be giving a keynote at that point.
Can I start?
Yes, please.
All right, great. Hi, everyone. I'm Min-Sung. I'll be talking about scaling decision theoretic probabilistic programming with factorization. So this leans less into the RAGSTER part of DRAGSTERS and instead into the D and the S part specifically. And so with that background in mind, let's talk about probabilistic models, which hopefully we can all agree is crucial in talking about real-world phenomena. And hopefully we can also all agree that the primary reasoning task that we do on these probabilistic models is something called probabilistic inference, where we want to give the probability of some event happening over the model. And in particular, we want support for things like Bayesian reasoning, where we observe some events happening on the model and then adjust our probabilities accordingly. So here's an example probabilistic model that we can think about. This is a diamond of network routers where each edge denotes a connection between the routers, and each edge weight denotes the probability of the connection successfully sending a packet. And perhaps an inference task that we can give is, given that router E received a packet, what's the probability that it came from the top route and not the bottom? So what exactly is probabilistic programming then? Well, it's a programming language way to specify these probabilistic models. Of course, the task is still probabilistic inference. That is, we still give the probability of some event occurring over bound variables of the program. And lastly, we also have support for Bayesian conditioning. So some popular probabilistic programming languages out in the wild today include Stan, Dice, and Problog. But for the remainder of this presentation, we'll be focusing on discrete probability. So what does the standard probabilistic program pipeline look like? Well, we usually go from a probabilistic model, perhaps a graphical model, straight to probabilistic inference. But when we're doing things, like when we want to add simple features like functions or adding random variables, for instance, this can lead to exponential blowup. So let's not go down this route and instead translate to a probabilistic program. Of course, programs are still models and we can still do inference on these programs, but to make inference more tractable and avoid this blowup that we see in traditional models, what instead we do is we'll compile to a Boolean formula with weights and then give that a probabilistic circuit representation. I'll get to in a little bit about what that is, and then on which inference is actually tractable. So let's see this pipeline in action and go from a model to a probabilistic program. So here's our network example from before. This is its corresponding probabilistic program. The flip keyword in the probabilistic program represents each uncertainty in the network router. So we can see that flip 0.1, for example, denotes the 0.1 probability of a packet being sent from router S to T. Same for 0.3, 0.7, and 0.4. And the rest is other code to finally establish the network. So we saw how we can translate from a model to a program. So what about everything else? Well, we can also go from a probabilistic program straight to inference, and we can go from a program to a Boolean formula with weights, straight to a probabilistic circuit representation. This is well studied in PL and AI, but the details are rather technical and frankly are beyond the scope of the talk in DRAGSTERS. But I'll be focusing on the circuit representation, going to probabilistic inference. This admits an efficient algorithm using purely semiring operations and is also the basis for a novel contribution. But to see it in context, let's see this entire pipeline in action. So here's our probabilistic program from before. What I mean by Boolean compilation is that we literally transform it into a Boolean formula. So for example, each if-then-else statement in the probabilistic program turns into a disjunction of conjunctions, and each flip becomes a Boolean variable. Same for the bottom route, which is also an if-then-else statement. And of course, XORs in the program become XORs in the Boolean formula. This long Boolean formula on the left can simplify into an XOR of conjunctions, which is then given a probabilistic circuit representation. So here's our probabilistic circuit representation. So it looks complicated, but let me try and explain to you what it is. So the leaves denote 1 and 0 truth values. The non-leaf vertices are simple variables, and their outgoing edges are either solid or dotted. Solid indicates the variable is true, and dotted indicates the variable is false. And the weights indicate the probability of the variable being true or false, respectively. The key invariant that I want to highlight in this is that the paths from ST to 1 represent assignments in variables of a formula that satisfy our Boolean formula. That is, it evaluates to true. So what does inference look like on a probabilistic circuit? Well, it's actually a 4-line for each non-root vertex going bottom to up. Let WV be the weights on the outgoing edges, and let PQ be the values of the child vertices, and then return WP plus VQ, and we do this bottom up. So let's see this in action. So first, let's do the bottom left BE. So that's 0.4 times 0 plus 0.6 times 1, that's 0.6. There one 0.4, and we can update accordingly. And we can keep going. TE becomes 0.41. And finally, we end up at 0.293. And a fact that has been proven in the literature is that the topmost node is actually the answer to an inference problem. And the key point here is that the probabilistic circuit represents semiring computations efficiently over the real semiring here, in the sense that we used each edge at most once. Whoops, there we go, okay. So now we have this theme that probabilistic circuits factorize semiring operations for fast inference. What other probabilistic tasks allow for factorization? Well, another probabilistic task that's frequently encountered in the literature is decision theoretic modeling. So we can have a decision theoretic probabilistic model, like an influence diagram, and we can go straight to something called a maximum expected utility calculation, where we try and find the set of choices to make that optimizes our reward. But this is intractable in the same ways that standard probabilistic models going to inference is intractable. So let's not go this route and instead take the probabilistic program pipeline approach. So we can go from a decision theoretic model to a decision theoretic probabilistic program. Of course, this is still a model, and we can still do maximum expected utility calculations. But to make everything tractable, how about we just also compile to a Boolean formula with weights, then give it a circuit representation, and then calculate maximum expected utility. So let's see this pipeline in action. Let's first look at a decision theoretic probabilistic scenario, translate it into a model, translate it into a probabilistic program, and then see how MEU might be calculated. So here's our network example from before. An alarm goes off at router E. It didn't receive a packet when it was supposed to. And us, we're a network administrator. We can choose to investigate either router T or B, and we choose to investigate router T. And we find out it's on fire. And since we found a faulty router that received the packet but didn't send it out when it was supposed to, because it's on fire, we received some financial compensation. So what language features did we encounter in this decision-making scenario that we need in a decision theoretic probabilistic programming language? Well, first is some sort of Bayesian reasoning, right? We want to observe events and condition on them. Next, we want a way for us to choose between choices, which I'm going to be calling decisions. And next, we want some notion of reward for us to distinguish which choices are better than others. All in all, we can translate this decision theoretic probabilistic model into this decision theoretic probabilistic program. I've truncated a lot of the probabilistic reasoning going on, but all of the key features of a decision-making language remains intact. In particular, we have observations / conditioning on events. We have choosing between choices, where choosing is denoted by the choose keyword, and choices are denoted within the square brackets, and each variable within is a choice. And we have a primitive notion of reward, which is additive. Now we can calculate what maximum expected utility might look like in our decision-making scenario. So let's make a decision tree. So we can choose to investigate router T, right? So we can either choose to investigate it or not. We can denote that as Boolean variables. And then we can choose to investigate router B. This is also a Boolean variable, which we can instantiate to be true or false. And then we get some expected rewards or utilities. Of course, some of these choices are invalid. In particular, I want to enforce that you can't neither choose T or B or choose both T and B, so those default to 0, but the rest have non-zero values. And we see that it's better to not investigate T and rather investigate B. And so us, the smart network administrator, thinks, okay, well, I should investigate T and rather investigate B. But we also observe that this tree is going to be exponential in the number of choices. It might be highly intractable once the number of choices that we need to make grows. So we've seen everything in action. We've gone from a model to a program and also done an MEU calculation on this model. So what about everything else? Well, I gave you a sneak peek of my decision theoretic probabilistic programming language and how it might how it looks like. These are actually all new contributions, and they're weighted by the expectation semiring, which we'll get to in a second. But For finer details, please check out my SRC poster on Monday. Instead, for the remainder of this talk, we'll be focusing on going to the circuit representation to maximum expected utility, which not only builds on prior work, but I'll also contribute a new algorithm for fast MEU. Of course, to see everything in context, we need to expand and see the whole pipeline in action. So what does compilation look like? Well, here's our decision theoretic probabilistic program from before. And this is the Boolean formula that it compiles to. Each observation, each conditioning on events becomes a conjunct in our Boolean formula. The choose gets in exactly one constraint to enforce the fact that we can't choose both decisions nor abstain from them. And the rest look like simple if then else or pattern matching, where you have disjunctive conjunctions on both sides. So what does compilation for this look like? Well, take our decision tree from before, and let's think about the scenario where we choose to investigate T and not B. We can, since we've given T and B Boolean variables, we can then condition our Boolean formula by them, in particular the assignment T being true and B being false. We get the simplified Boolean formula, which is then given the circuit representation. Notice how the edge weights and the leaves have changed their weights. We'll get to that in a second. These are actually values of the expectation semiring, which is a tuple of non-negative reals and reals, where 0 is just 0 in both coordinates, 1 is 1, 0, addition is coordinate-wise, and multiplication is multiplication in the first coordinate, and then something resembling a matrix determinant or a combination in the second. The algorithm still stays the same, though. So we can see this algorithm in action again. This is rather tedious computation, so I'm going to rush this along. And finally, we have that our ST node gives the value 0.05, 0.5. What we then do is pull out the second coordinate, which is our expected utility, and divide by Bayes' rule by the probability that our event occurred to get our correct expected utility. The key point here is that the probabilistic circuit represents expected utility given our decisions. Notice how we first fixed the choice that we're going to investigate T and not B. Cool. So how should we find the best given choices to calculate the maximum expected utility? Well, here's our decision tree from before and the associated expected utilities. We can do a branch and bound approach. So let's step through this branch and bound approach before first. So maybe we have this upper bound function that starts at the root, recurses down to maybe T is equal to false first, and then hits an upper bound point where UB is equal to 0, at which point we've encountered a leaf, and we update our lower bound accordingly. And then we recurse down to the other leaf, and we see that the upper bound is equal to 5.8. Since this is equal to the lower, then this is greater than the lower bound, we can update our lower bound accordingly. But we see that when we recurse all the way back up to the root, and instead look at the case where T is equal to true, we see that the upper bound is equal to 0.72. We see that, okay, well then in all scenarios going down, then none of the leaves will have value greater than 5.8. So we can successfully prune this decision, and then we have all of the computed values, and to just take the maximum of 2 values rather than 4. Cool. So sure, we can do this, but notice the intractability still remains the same. In the previous slide, where we have the decisions being exponential, right? So what if we factorize decision making also? So how do we do this? Well, maybe we start off with T, like normal, but then we do some partial utility / reward computation, still on a probabilistic circuit. And then we do B, and we branch on that. And then instead of comparing 4 values, we compare 3 values. So now we're interleaving probabilistic computation and decision theoretic computations at the same time. But how would our traditional branch and bound look like in this context? Well, it turns out it's actually just 3 extra lines on our standard expected utility, on top of our standard expected utility algorithm. These are the 3 extra lines. And so now we case on whether the vertex is a choice or not. If the vertex is not a choice, we do the standard thing of returning WP plus VQ. If the vertex is a choice, we return the maximum of WP and VQ, where the maximum is taken coordinate-wise. So to finish up my talk, let me give you some concluding remarks and themes. And so probabilistic circuits first provide a factorized representation of semiring computations. In particular, this is the instance of something called semiring semantics over Boolean formulas. And number two, semiring computations are actually an essential component in compiling probabilistic programming languages. And if you want to talk more about that, I'll be here. For more about our contribution, third, we provide a new algorithm on top of these probabilistic circuits that calculates maximum expected utility. And four, it's easily generalizable to a broad class of semirings, maybe hinting at a question, proven fully correct, and it also outperforms current state-of-the-art solvers. It's also implemented fully in Rust. Please check it out at this link. Great. Thank you so much.
So I realize people may need to do something during the break. If you need to run out now, please go ahead, but we'll take questions really briefly.
Thanks for the great talk, Vincent. Thanks for the great talk.
Hi.
So in probabilistic decision theory, I feel like a lot of times people look at trying to choose the best single action, one action at a time, or trying to choose the best policy, like a rule for choosing actions that's based on what's actually happened so far.
Right.
And it sounds like you're looking at sort of finding an assignment to all of the non-deterministic choices all at once.
Yeah,
Have you
correct.
thought about how this could extend to finding policies or that could depend on the state?
Yeah, sure. So this is something that, there's been recent observations from Gordon Plotkin and Martin Abadi where having multiple decision-making agents can reflect the branching scenario in which you've mentioned. The semantics of this is still up for future work, but this would be the first avenue that I would go to from a PL perspective to address that kind of issue. And yes, the current language that I have only supports the one-shot policy scenario. Yeah.
So can this extend to sort of concurrency? Like,
I'm not, so I'm not too well versed in concurrency.
but I mean, so
unfortunately.
example, I have two actors, and then I have a race condition, and then I just want to sort of, in my debugger, I just want to give high probability that it was because P1 came first.
Yeah, so I'm sure this is something that you can model. As long as you can represent it in some sort of Boolean function. In particular, this generalizes to a broad class of semirings that also have a lattice structure. And so I'm not sure exactly what kind of scenario you're thinking of, but we can talk more.
Thanks.
Yep.